Hello and welcome to the Callum Cymru revision session for A-Level Further Maths. My name is Matthew McMillan. I'm a teacher at Christ College in Brecon. Today we are going to take a look at calculus with hyperbolic functions. So there's already one video that I created on the basics of a hyperbolic function and then how to solve equations involving hyperbolic functions and then identities involving them. Today we're just going to look at the calculus involving them. So we're going to think about how to differentiate and integrate hyperbolic functions. And then also think about different substitutions that we might need to use when we're differentiating or integrating them. We'll start off with the basics of how to differentiate a hyperbolic function. Okay, so let's start by differentiating sine. If we take y equals sine x and just write it in exponential form, so you need to recall that because it's not given in the formula book, and we'll just break it up. Now, what we'll do then is differentiate this. So dy over dx gives us a half, and when you differentiate e to the x, you just get e to the x. And then here, because you're doing a minus times a minus, we get plus a half e to the minus x. Well, that is just the same as cosh x. So when you differentiate sin x, you get cosh x, and vice versa. These are given in the formula book, but it's worth remembering you can always go back to exponential form if you forget how to do it. So this is how they appear in the formula booklet, and these ones we can kind of do by differentiating the exponential form. I guess this one we could write this as sine over cosh, and then seeing that the derivative of the top is on the bottom, and going from there. The ones below there, we might need to be able to derive them. So we're going to take just this one here and try to derive it. So what we do have in the formula book is we know what sine of x is in terms of natural logarithms. So that's what I'm going to write, the inverse sine of x in terms of natural logarithms, and then I'm going to go from there. Now, the square root element, I'm just going to rewrite that as a bracket to the power of a half, just to make it a little bit more obvious how to differentiate it. So if we differentiate this now, so dy over dx, when you differentiate a natural logarithm, we get the original function on the bottom of my fraction. So underneath here, I'm going to get x plus x squared plus 1, all in brackets, to the power of a half. Okay, so that's the denominator. On top then, we get whatever the derivative of this function is. And so when we differentiate the x, that turns into a 1. When we differentiate this bracket, because we're kind of applying the chain rule here, that's going to give us, well, the power is a half. If we differentiate the x squared element, that gives us 2x. Then we've still got the bracket, so that's the x squared plus 1. And then we reduce the power by 1, so that becomes minus a half. That does not look like what it looks like in the formula book, so we're just going to keep going with this. Let's tidy up the numerator here. So what I'm going to do is break it up into 1 plus, so a half times 2x, that's just x. And then the fraction, sorry, the bracketed bit with the negative half power, I'm actually going to write that as over the square root of x squared plus 1. So all I've written here is the numerator, just in a nicer format. And then instead of saying divide by the denominator, I'm going to say we're timesing by 1 over that. So x plus square root of x squared plus 1. There we go, so that's the denominator. Let's take this left-hand bracket here. Instead of writing 1, what I'm going to do is I'm going to write the square root of x squared plus 1 over the square root of x squared plus 1. Okay, so that's the one element. And then plus x, so I've just combined the fraction there, still times this right-hand fraction, 1 over x plus the square root of x squared plus 1. And then it looks like we've got some cancelling because the denominator here and the numerator here, they cancel each other off. So this leaves us with 1 over the square root of 1 plus x squared, which is given in the formula book. But you may need to be able to derive it, and that's how we get there. So let's try a more straightforward exam question where we're just applying what's given to us in the formula book. So we're going to need to differentiate this because it says to find the normal to the curve, and then we'll need to find the negative reciprocal of whatever the derivative is. So I sort of homing in on this one here because that's the one that is in the question, and I just need to be careful with it. So if we find dy over dx here, and you might like to try this before I do it myself. So we want to differentiate what's in the bracket here because we're applying the chain rule. So if I differentiate what's inside there, I get -1, and then I'm going to times it by whatever the derivative of hyperbolic tan is. So that's going to be 1 over 1 minus x squared. However, the x squared is not an x squared, it's all of that little bit there squared. So it's 1 minus x squared like that. You do not necessarily have to, but we could tidy this up a little bit. We're going to get a -1 on the top, and then we're going to get a 2x minus x squared on the bottom. So to find your gradient of your normal, so gradient normal, we're going to flip it upside down, so we get 2 times 1.7 minus 1.7 squared, all divided by 1, and we're also changing it from a negative to a positive. That gives us 0.51. That's the gradient of the normal. Then we want to think at x equals 1.7. X equals 1.7. What does our y coordinate equal? Y equals hyperbolic inverse tan of 1 minus 1.7. That gives us negative 0.8673. I use the option button on my calculator to get that. If they wanted it in terms of natural logarithms, that is in the formula book as well. I'm just circling it down there. So we could give it in terms of natural logarithms. If we do that, this is what we get. Half ln 3 over 17. Either is acceptable. Then we just apply our formula, y minus y1 equals m times x minus x1. So we've got y minus, but we've got to be careful here because it's minus minus, so plus 0.8673 equals the gradient, which is 0.51, times x minus the x coordinate, which is 1.7. We could multiply it out, but that is an equation that is acceptable. We'll just have a quick look on Desmos to see what that looks like. Okay, so we have the inverse hyperbolic tan graph shown, and I just thought I'd show you that because it's useful to remember that that's what that looks like, the green graph there. So I'm superimposing the actual function that we're dealing with. So inverse hyperbolic tan 1 minus x. Compared to the green graph, we can kind of see that it's going to be, well, the minus x is going to be reflecting it in the y-axis, and then the 1 here, that's going to be adjusting the position of the green graph. I'll turn the green graph off now. Our normal to that curve is there. So we can see it's cutting at this point here, 1.7, and it should be going at right angles to that point. I'll just zoom in so we can have a look at it. I guess because I have done a little bit of rounding with my decimal places here, it's likely that this isn't perfectly accurate, but that's acceptable for the exam board. Okay, so let's have a look at a slightly trickier one. This is from a more recent exam paper. It says differentiate each of the following, because there was a part 1 to this question, but I just skipped to the hyperbolic one. So we're differentiating the natural log, and then we've got this hyperbolic function inside there. Now, there is a kind of a nice, elegant way of going about this, but I'm going to show you probably where you might head to first. So differentiating the natural log, if we have a natural log of a function, when we differentiate that, that's going to give us the derivative of the function on top, and then the original function underneath. So I kind of want to look at the function that's inside my brackets and then differentiate it. So let's take the f of x as cosh squared 2x squared plus 7x. Now, there's quite a lot going on here, so I'm going to be thinking of the chain rule. I'm being a bit loose with the notation here, but let's say that this equals cosh u squared, and u is 2x squared plus 7x. So differentiating the u element here, du dx, that's okay. That gives us 4x plus 7. Differentiating this bit over here, dy du, that feels a little bit more awkward. I need to be careful here because I kind of could apply the chain rule again, which I'm actually going to do kind of up here. So I'm actually going to say that here y equals v squared and v equals cosh u. And then if I do dy by dv, that gives me 2v, and then dv by du, that gives me sine u. So down here, my actual derivative here, because I'm multiplying these two elements here, so that's going to give me 2, and then v was cosh u, and dv du was sine u. Now, this bit here, we do have an identity that we could change it to. I was tempted to change it to this. It looks like this, sine to u. However, it cancels off nicer if we leave it as it is. So we'll write down what our final derivative will look like here. So f dash x would look like this. It's going to be, oh, it's not very nice. 2 times 4x plus 7 times cosh u. However, the u isn't a u actually, is it? It's a 2x squared plus 7x. 2x squared plus 7x. And then the other bit, the sine, also has a 2x squared plus 7x in it. Okay, so that's what the derivative is. And then we just write the derivative over the original function. So dy over dx equals the whole thing that I've just written. I feel like I kind of want to multiply this bracket out. I guess I don't have to actually. Let's leave it as it is. 2 bracket 4x plus 7 times cosh of 2x squared plus 7x times sine 2x squared plus 7x all over. It's quite hard to get a straight line here. There we go. Cosh squared 2x squared plus 7x. That's the original function. So we have got the derivative on top and we've got the original function underneath. I can see there's some cancelling here, so the cosh bit up here cancels with one of the cosh bits down here. So this tidies up a little bit more, gives us this 2 bracket 4x plus 7 times sine of 2x squared plus 7x over just one of these, cosh 2x squared plus 7x. And then I can actually see that this sine over the cosh, maybe this would be nicer if I wrote it like this, 2 bracket 4x plus 7 times hyperbolic tan of 2x squared plus 7x. Although actually the mark scheme didn't say you had to get that far. There is an elegant way of doing this. So if we go right back to the beginning up here, do you see the squared there? That is affecting everything. So what we could do using our log laws is we're allowed to bring that to the front here, to ln, and then you get cosh of 2x squared, 2x squared, sorry, plus 7x. If you try to differentiate that, that is a lot easier. Okay, both of those ways are acceptable. Okay, so that's a slightly more difficult question, differentiating a function involving hyperbolic cos. Okay, so we'll just look at one more differentiation question. Find the equations of the tangents to this curve. And this time it's x equals something rather than y equals something. Now I'm just going to rewrite this as x equals the inverse sine of u, where u is y squared. And I'm going to differentiate here. Normally we do dy over du. This is going to be dx over du. So using my formula book, I'm looking over here, this is 1 over the square root of 1 plus, but it's not a u, and it's not an x anymore, it's a u. So 1 over the square root of 1 plus u squared. And then over here, du dy is 2y. And then I'll use the product rule, the chain rule, and multiply the two together. So that's going to give us dx over dy equals 2y over the square root of 1 plus, now because u was actually y squared, if I'm doing u squared, that's actually y to the power of 4. So that's our dx over dy, but we want the gradient, so to get that, I want dy over dx. So it's just the reciprocal of what I've just written, 1 plus y to the power of 4 over 2y. Okay, so we've now got an equation to represent the gradient. Now, again, I would be probably wanting to put the y into here, so I want to have a think about this. At x equals 1, because that's the coordinate they've given me, 1 equals the inverse hyperbolic sine of y squared, and I'm just going to have a little rearrange of this. So y squared equals sine 1, so y equals plus or minus the square root of sine 1. Okay, so I have got a value for y now. If you put this in your calculator, you get plus or minus 1.084 ... That then, I have the value that I can substitute into here. So dy over dx, or the gradient, is, if you put the plus in, you get plus 0.7117. And if you put the minus in, you get the negative of that. That then gives us our equation. So we get y minus 1.084 equals the gradient, which is 0.7117 times x minus 1. So that's using y minus y1 equals m times x minus x1. But I'm getting two values for y, and I'm getting two values for my gradient. So we also have another equation, y, and we're doing minus minus, so that's plus 1.084 equals minus 0.7117 times x minus 1. What we'll do is we'll just have a look on Desmos to see why we're getting two tangent equations there. Okay, so we've plotted the function. This is what it looks like. You can kind of see why we might get two tangents. I'll turn both of them on. Okay, there's a tangent there, and the other tangent, you can see we've got R1 here, which is what we were interested in. The other tangent is here. Now, we did do a lot of rounding because we have a load of decimals here, and obviously these would be exact values. So actually, when we look on here, it's telling me that that is actually not touching at x equals 1, and down here it's not actually touching at x equals 1. But that's just due to the amount of rounding that we've done in our answer. We should be more up here somewhere. That's where they should be touching, but it's fine for the accuracy of our answer. Okay, so we're just going to look at integrating functions now. We have a long page of integrals, so you don't have to learn any of these per se, except it's probably worth learning the exponential definitions and how to integrate them. It's also worth remembering that we do have the differentiation page. So when I have a look at this, for instance, this one here, if we integrate it, because we know it's just the reverse of differentiation, it will take us back to hyperbolic tan. And when I look over here, I sort of scroll down, looking down here, it is not available as an option. So sometimes you don't have an option showing you how to integrate something. You then want to look back at the differentiation page because it might be there. Some of you will say, well, I can see that it's just going to be the same as what that is, but I guess it's not explicitly written there. Let's move on and have a look at some exam type questions. Okay, so we have a reasonably straightforward integration question to start with. I've given you a clue by putting what the rule is on the side. This is looking like integration by parts because we have two functions multiplied together, and we want to be careful with what we're going to choose for u and what we're going to choose for dv over dx. Usually you choose the thing that's going to differentiate and reduce each time, so we're going to set u as x. That will give us du over dx as 1, and then dv over dx, we'll set that as sin x, and then when we integrate that, we get cosh. I'm going to just deal with the integral to start with. So the integral, if I follow the rules, it's u times v, so that's x cosh x, minus the integral of v times du over dx. Well, v is cosh x, and then du over dx is just 1, so I don't really need to write that. Let's just go again because I want to integrate the thing on the right hand side. So x cosh x minus sin x. Technically I'd have a plus c here because I haven't actually put my limits in. I could then go and put the limits on top of this so that we get x cosh x, and we're going to integrate between the two limits now. Between 1 and 0. We want to show the answer. I can see that we're getting something involving e, so at some point I'm thinking I need to get my exponential definitions involved here. I'm not going to do it just yet. I'm going to write this, so cosh 1. I've reduced the x because it's 1, so x is 1 times cosh 1 is just cosh 1, minus sin 1, so that's substituting in the 1, minus, and then we're putting in a 0, so it's 0 times cosh 0, minus sin 0, Oh, I've put a theta in there by accident. 0. This bit here, that equals 1, although it's going to be multiplied by 0, so it'll equal 0. And this bit here, this bit equals 0. So effectively this whole bit just kind of cancels itself off. And then we're left just with the left-hand side. Now I'm going to change these for the exponential definition. So this is going to be e to the power of 1 plus e to the power of negative 1, all divided by 2. That's what the cosh of 1 is. And then for sine, we get e to the power of 1 minus e to the power of negative 1, all divided by 2. This then gives us, well, e to the power of 1 minus e to the power of 1, they cancel off. E to the power of minus 1 minus minus e to the power of minus 1 gives us 2 e to the minus 1s, all divided by 2. The 2's are going to cancel each other off, and that gives us e to the power of negative 1, which is 1 over e, which is what they said it would be. Let's just take a look at Desmos. It's worth just remembering as I look at that, this is equal to 0.367 something or other. And you could use the integration button on your calculator just to check that that is what you're getting there. Let's look at it on Desmos then. Okay, so let's type the function in. I'm just going to type in shinex to start with. So that's the purple purple line that we can see. I'll just pop it back up. If we put an x in front of this, you can see it kind of turns into, looks like a parabola maybe. And then if I adjust my limits here, so the bottom limit was 0, so I'll just bring that to 0. There we go. And then if we bring this upper limit down to 1, we get 0.367, something like that. So that is the area that we found. That is equivalent, equal to 1 over e. Interesting that it looks like cosh x. Let's, just for interest, just type in cosh x just to make a comparison. That's the blue line there. I wonder what's going to happen if I put an x in front of that. There we go, it kind of looks a bit like shinex, which is interesting. Anyway, that's what we get. Okay, so let's have a look at a slightly harder integration question. It's an integration by substitution, which is quite common. This one, they've given us the substitution, which is nice. So we've got x equals sine u. I can see I've got an x squared there, so I'm just going to square this. X squared equals sine squared u. And then we also want to think about replacing anything involving an x. So I need to find out what dx by du is. Dx over du, that's cos u. And that then implies, because I need to replace the dx element, dx is equal to cos u du. There's one more thing that I need to remember to replace, and that's the limits. So the limits at the moment in terms of x are 0 and 3. I need to change them into something involving u. This one here, well, I'm just going to write inverse sine of 0, and this one here is inverse sine of 3. This here just equals 0, so I'll just write 0 from now on. This other one equals some horrible decimal, so I'm not going to write that. I'll just write inverse sine of 3. So our integral, that becomes this. Integrate between inverse sine of 3 and 0. And then the numerator, instead of x squared, we've now changed it to sine squared u. And the denominator is the square root of sine squared u plus 1. And the dx is now cosh u du. At the moment, this is not looking particularly nice. It doesn't look like it's any easier, but let's keep going. So we are integrating, we're still going to keep these limits, so shine -1 of 3 and 0, and we're still on the top here, we're getting shine squared u cos u. On the bottom here, this bit here is the same as cos squared u, using one of my hyperbolic identities. So we're actually doing the square root of cos squared u. That's just going to equal cos u du, and suddenly this is starting to look a little bit better. Those cos disappear. So we're just integrating shine squared. We can't integrate something squared like this, so we need to use an identity. And just recall that the identity, I'll just write it out here, that is equal to 1/2 cos 2u minus 1/2. We can integrate the one in red, we cannot integrate the function in blue, so we're going to rewrite it as that function. This then, we're integrating between the inverse shine of 3 and 0, and we're changing it, in fact I'm going to pull the 1/2 out, we're changing it to cos 2u minus 1 with respect to u. So that's our integral. If we do that, we'll keep the 1/2 out the front. So the cos turns to shine, and we've got a 2 involved, so we need to bring that to the front when we integrate, and so we divide by the 2. So we're getting 1/2 shine 2u minus, and then the 1 is turning into u. We do not need to turn it back into x because our limits are now in terms of u. So shine -1 of 3 and 0. If you do turn it back into x, you could do just a bit of a waste of time, but you'd have to make sure you're using 0 and 3 there. It doesn't say it wants it in a particular form. Oh yes, it does. Sorry, it says it wants it to 2 decimal places. So that means we're going to write 3.83 to 2 decimal places. So that's an integration by substitution, but it's quite nice because they gave us the substitution. Now, another thing that the specification talks about is being able to choose the correct substitution. So here they're telling us that they want to be able to integrate functions in this format, which is a little bit like what I had before. But we need to choose the correct substitution. So the x squared plus a squared, the x squared minus a squared, we're thinking about these identities that we should be learning. This question here might be an example of it. I can sort of see here this x squared plus 4. It's a little bit like this. The power there is a bit like the square root symbol that's here. And I noticed that it's something squared plus something, so that's kind of making me home in on this. This is something squared plus something. In this exam question, I've actually taken it off a past paper. They did give you the substitution for this one, but the specification is suggesting that wants you to think, what would I do if I didn't get given the substitution? So we're just going to have a think about that now with this question. Okay, so when I look at this question, I'm kind of looking at this bottom bit here, the x squared plus 4. I'm just going to write that over here. I can sort of see it as something squared plus 4. So I'm looking over here at this bit here. It's shine squared x plus 1. So I need to somehow make that 1 turn into a 4. So I'm just going to kind of times this by 4 and just see what happens. That would give me 4 shine squared x plus 4. And I need to make sure that this whole thing here is being squared. At the moment, only the shine bit is being squared, not the 4, so I kind of want to combine that together. If I did this, 2 shine x all squared plus 4. That 2 squared would give you the 4, and the sine x squared would give you the sine squared x. So I feel like I've got this now in the format. That bit there is the x bit, and that 4 is the 4 bit there. So I'm sort of thinking the substitution is going to be x equals 2 sine u. I should have probably used a u throughout all of this, but that looks like my substitution. So that's what I'm going to have a go at using that. I'm going to rewrite it over here. So x equals 2 sine u. We are going to want to differentiate this. So dx over du gives us 2 cos u. That then implies that dx is 2 cos, oh, I've left a u there, is 2 cos u du. And then I also want to deal with the limits, the 0 and the 2 here. I might just want to have a think here about what u is. U is equal to the inverse sine of, it looks like x over 2. That'll help me get my limits correct. Let's just think about the limits then. So when x is 0 and 2, u is going to be, well, if you put a 0 into here, we're going to get a 0 coming out. And when we put a 2 into there, we're going to get an inverse sine of 1. Okay, so those are my limits. I think I've got all the bits that I need to do my substitution. So let's write this down. So our integral is looking like this. Integrate between the inverse sine of 1 and 0. The dx bit on the top is going to become 2 cos u du. I'll write the du at the end. Over, and then underneath we're getting 2 sine u all squared plus 4, all to the power of 3 over 2, and then we'll put the du there. Let's keep going. So we're going to integrate between sine minus 1 of 1 and 0, and we've still got the 2 cos u on the top. On the bottom here, I'm going to pull out the 4, so I've got a 4 because I could see that the 2 squared gave me the 4. So I pulled the 4 out, and I'm just going to write the sine squared u there. I'm also pulling the 4 out of this bit here, so I get plus 1. All of that is still being affected by the power of 3 over 2. And I think we'll just do one more step of working here. Actually, there's going to be 2 more little steps here. So we integrate this, we get inverse sine 1 and 0, 2 cos u on the top. On the bottom, so now I'm having a think about what the power is doing to each of these bits. And the other thing I want to have a think about is this bit here is where I'm going to stick my identity in. This is going to give us cos squared u. So we get, well, 4, because the denominator of our power here, so I'm just concentrating on that bit, the denominator is square rooting it, and then we're cubing it back up, so we get 8. And then for the cos squared element, this bit here, the denominator is square rooting it, so it's going to turn it to cos, and then the numerator is going to be cubing it, so that's going to give us cos cubed u du. I've got a cos on the top and I've got a cos cubed on the bottom, so I'm going to kind of cross that one off and cross one of those off to leave with the cos squared on the bottom, and I'm going to just continue kind of up here. It'd be nice if you could just continue down the page if you were doing this. So this gives us integral between sine minus 1 of 1 and 0, and we've got, actually let's break this all up now. So I can see that this bit here, the 2 over h, that's going to give us a quarter. And the other bit, the cosh squared that's on the bottom, let's rewrite that as the hyperbolic set. So sec squared u du, like that. This then is where I need to look in my formula book, and it's what I mentioned earlier. You don't get given all the integrations, you need to look at the derivative page. So if I know that my derivative of tan x takes me to the hyperbolic sec squared, I can work backwards and use that fact. So this, when I integrate this, it gives me a quarter tan u between the inverse hyperbolic sine of 1 and 0. If you put these values in, you get 0.177 to 3 significant figures. Actually, it does say it wants it to 2 decimal places. I guess I've given that. So that's a little bit harder, having to choose your own substitution, but they are saying that they would like you to be able to do that. So that concludes the video on differentiating and integrating hyperbolic functions. We have just had a look at how to differentiate some of the basic functions, but then also taken a look at some of the more tricky exam style questions. We've also had a think about how to integrate functions given in a certain format. My main piece of advice would be to use your formula book and have it with you during all of your revision and all your past paper practice, because it's really, really helpful. So that concludes the calculus with hyperbolic functions video. As I mentioned before, there is a basics of hyperbolic functions video. There are also videos for further maths on polar coordinates, trigonometry, matrices, as well as some of the AS level content as well. Please do visit the Kalam Cymru website to see more revision videos, not just for further maths, but for many other subjects at both GCSE and A-level.